Okay, this is section 4.3 on logarithms and logarithmic functions. Doesn't roll out of the mouth very well. So let's go ahead and start in. So exponentials and logarithms. We know that they are inverses of each other from what we'll show next. So we should remember though that exponential functions are of the format of f of x equals b to the x power, and if b is between 0 to 1, remember b can't be negative, it's just a reflection, so we'll just assume that it's positive. If it's between 0 to 1, it goes down, right, as a decreasing function. Then if b is above 1, remember 1 is trivial, so we don't count that one, it goes in an increasing fashion. Okay, so that's what we should remember from exponentials. Now, can we find an inverse function of an exponential? Well, yes, because it passes the horizontal line test, meaning all points are 1 to 1, right? So then, what is the inverse, right? Well, the inverse must exist because, well, we just said it could, right? Graphically, we can just switch x and y, right? So the domain will become the range, and the range becomes the domain. And the inverse graph will just be a reflection around the y equals x line, just like this in this picture, right? So this pink line, right, that's our exponential. That's y equals 2 to the x. Then this blue line is the logarithmic, or the inverse, okay? That's the x equals 2 to the y. We literally just switched them around, right? So now let's go from there and talk about logarithms. So now we know that it's kind of switched around, right? B is still greater than 0 and not equal to 1, but now we have that x has to be greater than 0, because think back on the graph here of an exponential, its range was greater than 0, right? So we switch it around, we now know our domain is greater than 0. Okay, then the range was the domain, and before with exponentials we could plug in anything we wanted, right? So now with the range we can now get anything. So then we had an asymptote at x equals 0. Y equals 0. So now this is at x equals 0. Right? Then the common points are 1, 0 and b 1. Okay? So before it was you plug in 0, you get out 1, right? For the exponential. So we just switched it around. Then we plug in 1, you get the base of b. So again, just switched around. Okay, so that's the kind of basic things about a logarithm. So how do they work together, right? How do you convert between one and the other? This is kind of what it looks like, but let's actually convert them and see kind of how we go between them. So there's a couple different ways we can think about it, okay? So if we have y equals b to the x, we want to get to this setup. So there's the way of just converting, knowing how it works, or using log as an inverse function. So that means, let's do that one first. That means we would take log base b. It has to have the same base. That's very important. Take log base b of both sides. So log base b of y is equal to log base b of b to the x. Now, base b log and base b exponential cancel to just leave us with x on that side. That is exactly what we wanted here, right? Now, the other way is to think that we could also just know how they work, all right? So that means if we think about this one here, we want to go backwards. It's base to the answer equals the inside. So base, right, to the answer equals the inside. Okay? So base answer equals inside. So if we want to start here, well, inside equals base answer. So log base b of y equals x. Okay? Or this is kind of like same base, it's log of the base, right, of something, right, equals the exponent. So that must mean that this is the answer, right? So, or you could think about this is the kind of, this could be y there, could be b to the x. It doesn't really matter, okay? We'll talk about that a little bit more as we go through. But the easiest method to use as you're getting used to it is this first one that we did here, okay? Knowing this stuff just kind of happens as you get used to it and you see the pattern, all right? But until you're really used to it, I would just use this one, okay? So now that was kind of any log, right? But what about when the base is in e, right? So that is called a natural base or a natural log, okay? So we can still convert directly between them just like we did with basic other logs, any other base, right? So let's see how we convert with these. Let's do this one the other way, okay? So it works a little bit differently. So if we have x equals natural log of y, we want to get rid of the natural log. So its inverse is e, okay? So that means we'll raise both sides within the e power. So that means e to the x equals e to the natural log of y, okay? So then e and natural log cancel, so that means e to the x equals y. That's exactly what we started with, right? Or kind of wanted to get to. So now also one other thing to point out, if a log does not have a base written, that is an understood base 10, okay? Most commonly we use base 10, okay, kind of in the real world, because, well, we have 10 fingers, right? So we're base 10 kind of thing. That's how we think. So let's move on and do out some problems, okay? So this one, what this would be is you want to think about what would be here, okay? So think about this. You can do it 2 to both sides, right? So log base 2 cancels. So then we get 8 equals 2 to the x, and then you have to get same base. So 8 is really just 2 to the third equals 2 to the x. So then that's that exponent rule, that if we have the same base, then the exponents must equal. So that means x equals 3, okay? We can do the same thing here, or we could use that conversion, right? 5 to the answer, right? Base to the answer equals the inside. So 5 to the x equals 1 over 25. Well, this can again be rewritten as 5 to the x equals, well, 25 is really just 5 squared, but it's in the denominator. So it's 5 to the negative 2. So then x equals negative 2. Now this one seemingly looks a little odd, right? But let's just treat it the same way we've been doing. So e to the x equals e. Well, that's e to the first, right? So that means x equals 1. Okay, same thing on this one. 10 to the x equals square root of 10. So then 10 to the x is equal to 10 to the 1/2. So x equals 1/2. Okay? Those are pretty simple, right? You're just doing little basic things to them. So now let's think about the graph of a log. Now let's remember our kind of basic points that we had, right? We will always have, to start out with at least, 1, 0 and B1, okay? So now let's go back to our graph problem. These are just transitions, right? Transformations of the graph. So think about our points. We have 1, 0, and sorry, I'm just blanking here for a second. Our other point is if we plug in base 2 to the answer is equal to the inside. So we want it to be our points here. We have 1, 0 and B1. So, okay, 1, 0 and B1, so 2, 1. There we go. I don't know where my brain went there for a second. So, those are our points to start off with. Okay, these are not necessarily points on this graph, right? But they're points on the parent graph, remember, from previous chapter. So, if we think about what these transitions do, this one is a phase shift, right? It moves the points or the whole graph. Which direction? Well, it affects the x, right? And remember, when we affect the x, we go the opposite. So -3 actually goes to the right. So it's kind of like a +3 almost. So that means it changes our x's, right? If we want, we could also plot points. Plot these points of 1, 0 and 2, 1. And then we have our asymptote, right? And then we would have our basic graph, kind of like that. Not exactly, because that's kind of an ugly looking graph, but basically. Then we can think about what these points, these changes do. So the +3 on the x's, right, means that this transitions into a 4, and this one transitions into a 5. All right, then this +1. The +1 is what? It's a vertical shift, right? Vertically affecting the y, we don't change that. That just does exactly what it looks like. So that just goes up 1. So 0 becomes 1 and 1 becomes 2. Now our asymptote is now no longer on x equals 0, it's on, well, we added 3. So it's on x equals 3, right? So now we have our asymptote here. We have our point at 4, 1, and we have a point at 5, 2. So you'll notice it shifted over and up a little bit. That's exactly what those transitions meant, right? That's all we have to think about. If you're kind of unsure on doing it this way, that's fine. There's always multiple ways of doing these problems, right? You must, however, think about the asymptote. Start there and then plug in points, right? That will always work. If you know the asymptote is 3, at x equals 3, then plug in x equals 4 and x equals 5 and see what they give you, right? That's exactly kind of what we ended up with, but it's just a different way of thinking about it, okay? And if you're unsure, maybe if there's a reflection or anything, maybe try plugging in x equals 2. See if you can do that, right? Well, 2 plugged in, 2 minus 3, that's -1. Remember, our domain for logs needs to be positive, right? So we cannot plug in 2. So He's crossed off the list, basically. Then we would get our values for x equals 4 and x equals 5. Okay? So now, next example. We want to find the domain of the function. All right. Well, our domain, remember, means that the inputs within the log need to be positive. So that means that 9 minus x squared needs to be greater than 0. Just solve it out, right? So that means that negative x squared is greater than negative 9. So x squared is less than 9. So x is less than 3. And then for the negative portion, remember, you switch the sign again to get negative 3, right? Because you take the square root, you normally get plus minus 3. But the plus goes same way, the minus switches, okay? Just like when we did here, we divided by negative 1, so we flipped the sign, right? So in interval notation, this would be less than 3, but greater than negative 3. Not inclusive, right? Check something in between and check something on the outside just to make sure. If we plug in 0, always pick the easy things, right? 0 squared is 0. 9 minus 0 is 9. We can plug 9 into a log. Sure, why not? Let's try 4 then. 4 squared is 16. 9 minus 16, that's negative. We can't plug in negatives, so this is correct. Okay? So that is 4.3, all about kind of the basics of logarithms and kind of what you can do with them in converting between exponentials and logs, or the other way around, logs to exponentials.